So cyclic photosynthesis, the electrons return to the chlorophyll, that's your cycle. We did not do that one. We did non-cyclic. The electron that you saw ended up in the NADPH, and then off it went into the Calvin-Benson cycle. By the way, I know I keep saying just one more thing, but I still have one more thing, I guess. The actual products of photosynthesis are glucose and oxygen. Let me remind you of that formula. You've seen that before several times actually. Carbon dioxide plus water is producing glucose and oxygen. It's a reduction pathway. Carbon dioxide is being reduced to form glucose. That's your photosynthesis. I also want to remind you that respiration is the same exact formula, except backwards. So photosynthesis is a reduction pathway. Respiration is an oxidation pathway. The products for photosynthesis will be glucose and oxygen. The products for the light-dependent pathway is oxygen, ATP, and NADPH. Okay, now I'm really done. So, let's polish off this chapter finally. So nutritional patterns, we're back to this again. This is just a reminder, phototrophs get energy from the sun. Chemotrophs get energy from somewhere besides the sun. So really, inorganic or organic sources. Autotrophs get carbon from CO2. Heterotrophs get carbon from organic sources. Remember, with molecules with carbon, you only have two choices. Either the molecule is carbon dioxide or it's an organic molecule. Those are your two choices. So that, as you quite well know, we put these together in different combinations. The photoautotrophs are the photosynthesizers. So energy from the sun, carbon from CO2. By the way, I can now tell you that in doing that, in taking energy from the sun, what photosynthesis is doing is changing radiation energy into chemical energy. Is changing radiation energy into chemical energy. See, we obviously cannot use energy from the sun. Yeah, we'll go out and get warm, our skin will darken and stuff, but we're not really using the energy. We can't. But then photosynthesis changes that energy into glucose, which we can use. So again, the comment is that photosynthesis is changing radiation energy into chemical energy.
Okay.
Radiation energy, of course, coming from the sun, and the chemical energy meaning that that energy ends up in glucose, which of course we use all the time. Okay, so photoautotrophs. So photosynthetic bacteria, mostly oxygenic, but we also have the sulfur bacteria. They would be anoxygenic. Cyanobacteria, also called blue-green algae. Here I just have algae, but really green algae. There are many algae that do not do photosynthesis. The green algae are the precursors of green plants. They got the same general molecules and all the rest of it. They are the same green plants. They became the green plants. All of these are photosynthesizers. In most cases, oxygen is given off, so oxygenic. So, you know that, oxygenic. And sometimes anoxygenic, particularly for the sulfur bacteria. The sulfur bacteria, we use H2S instead of H2O. So in using H2S, the product will be sulfur and not oxygen. That's not a balanced reaction. I don't remember what it is, but I think I have to add water in there somewhere, but I forget. So anyhow, they use sulfur compound, H2S, sometimes rarely hydrogen alone, but that's not very common. So to produce sulfur, the sulfur can be oxidized in the atmosphere to produce sulfate, but essentially anoxygenic. The purple sulfur do the same thing as the green sulfur bacteria, just a different pigment, so a different color, but the same general everything. Photoheterotrophs, now they're also getting energy from the sun, but their carbon is coming from some organic molecule. It's not coming from CO2. So organic molecules, alcohols, fatty acids, not so often proteins, not so often, but fatty acids, alcohols, and also carbohydrates. So just a couple of examples, in honesty, you don't need to remember them. Green and purple non-sulfur bacteria, Chloroflexus, Rhodopseudomonas. Just a couple of examples, don't worry about it. Photoheterotrophs are mostly bacteria. As you've seen, the photoautotrophs, a lot of bacteria, but also lots of other stuff too. Chemoautotrophs. Nitrogen and sulfur compounds are commonly used as energy donors. Now remember what energy is. It's electrons. So in being an energy donor, they're actually donating electrons. That's what they do. They're electron donors. And both nitrogen and sulfur are rich in electrons. They both have unshared electrons. So the extra electrons can be donated. In donating electrons, they're donating energy. So the chemoautotrophs will frequently use inorganic molecules as energy donors, as electron donors. And these guys also mostly bacteria. A nitrobacter uses nitrite. So again, a nitrogen compound. NO2 is a minus charge. And the final category are the chemoheterotrophs. That's us. So we get both our energy and our carbon from the same source. We call it food. But it's organic, so we're getting carbon, and of course gives us energy. Now, all animals are chemoheterotrophs. So all the animals, and again, lots of bacteria. There are bacteria in every single group. But all the animals are chemoheterotrophs. So your two largest groups are the photoautotrophs and the chemoheterotrophs. It's not because of us, it's mostly because of insects. Saprophytes. Now, these are chemoheterotrophs, they're animals. They live on dead organic matter. And I have to tell you, I leave that in there as a constant reminder to myself that things don't always come out like I think they're going to. In other words, we've all had that experience. We've said something, we had something in mind, but the other person interprets it differently. It came across differently. We've all done that. This was such a case for me. A saprophyte, a true saprophyte, is like a spider, for example. You probably don't know this, you probably don't want to know it, but as you all know, spiders have spider webs and stuff, and they catch flies. When they're ready to eat the fly, what they do is they spit on the fly. And then the digestive enzymes in their spit, in their saliva, if you will actually digest the fly outside the body. And then when the fly has been digested, the spider simply sucks up the digested fluids. It's a little bit on the gross side, but that's a saprophyte. So that's what I was trying to say. So a year or two ago, I made that same comment, and some girl asked me, well, does that mean we are saprophytes? And my first reaction is, no, we're not saprophytes. My second reaction was, uh-oh, because I realized, based on that definition, when was the last time any of you ate a living animal? Probably never. Yeah, we don't eat living animals. But that's kind of what I said there. We all think food comes shrink wrapped, but obviously we eat dead organic matter as well. That's what we eat. So I've always got that in there as a reminder to myself that on midterms and other things, it doesn't always come out the way I think it's going to.
So we aren't.
No, we're not. We're not spiders. Other things do a similar thing, like starfish actually extrude their stomachs. They extrude their stomachs, and then they eat whatever it is while it's outside, and then they bring their stomach back in. That's a little on the gross side too, actually. Parasites. Also chemoheterotrophs. These are, well, not always animals. They could be bacteria. But a good parasite does not kill the host. The parasite's living on the host. It wants the host to keep living. So a good parasite does not kill the host. A tapeworm is an example of a parasite. I used to think it'd be really neat to have a tapeworm. Because as you know, the tapeworm inside will eat all your nutrition and everything, and you can eat all you want, you won't gain any weight. And people like me, losing weight is a good idea. So I thought a tapeworm would be a great idea. Unfortunately, I actually saw a picture of a tapeworm, and that changed my mind. And I meant to have it here today, but I don't. I'll try to find it for you. But it's unbelievably ugly. And it also hooks into your intestines, and it doesn't let go. So you end up with cramps and everything, and it's actually better to lose weight in some other fashion. So, anyhow, finished. Finished tonight for sure, but like I say, total maybe hour and a half at the most on this one. And essentially, all healthcare people, we want to kill bacteria, but in order to do that, there's an old saying, know your enemy. So in this case, we have to know what bacteria need to grow and to survive so that we can kill them. And so these are different factors necessary for bacterial growth. And it may not be the most exciting thing in the world, but you will find it a lot easier than what we just finished. You're through the worst. So temperature is one factor. And we have psychrophiles. That suffix phile means to like or to love. So for example, a pizzaphile, like pizzas. In this case, psychrophiles like the cold. Psychrophiles like the cold. And more specifically, they live in Antarctica and in your freezer. Notice they like 0 to 15 degrees. Now, I want to talk to you about that. This would be off the record here. I didn't know that kind of stuff. Now, there are formulas, and you've all seen them. There are formulas, and I can't use them. It's something like 9/5 Fahrenheit equals, don't use it. I don't care. But it will, you'll be using these temperatures forever. And if you ever travel, you will be in metric land. So it's not bad to be able to actually know what these temperatures are. So what I started with is the freezing point of water. So in centigrade, of course, obviously 0 degrees. And for Fahrenheit, 32, again, totally off the record, so if you don't want it, don't use it. So 32 degrees. Now the boiling point, 100 degrees, and 212. See, right away you can see why it's easier, right away. But at any rate, so what this means is the temperature range from freezing to boiling for centigrade is 100 degrees. For Fahrenheit, it's 180 degrees. We're going from here to here. So what? Now, please understand, I am not saying that 100 degrees centigrade equals 180 Fahrenheit. I'm not saying that. I'm saying that the temperature range of 100 degrees equals 180 for Fahrenheit. So there's a difference there. Okay, so divide by 10. Divide by 10. So what that says is, again, temperature range, 10 degrees of centigrade is 18 in Fahrenheit. Now that's what I want to use. By the way, if I were to divide again by 10, divide by 10, divide by 10, 18 over 10 is the 9 over 5. That's where that 9 over 5 comes from. But I want to stick with the 10 over 18. Let's use that. Or 10 and 18. Again, temperature range, not the actual temperatures. So what I want to do now is to take 10 degrees centigrade, but 10 degrees of centigrade is 18 of Fahrenheit, adding temperature. So add 18, so 10 degrees centigrade is 50 Fahrenheit, add 10, add 18, 68, add 10, add 18. So every 10 degrees of centigrade will give you 18 of Fahrenheit. But keep in mind, you've got to start with the freezing point of water, meaning 0 and 32. And then you add your numbers. Okay, now that's just exciting as can be, I'm sure. But the fact is, most times your temperatures won't be exactly on the tens. Maybe it's 35 degrees. Well, I'm sure you can figure out, if 10 degrees corresponds to 18, 5 will correspond to 9. So add 9, and that gives you 95. So you can get a little bit closer, but you're still kind of hopscotching around there. Let's say you have 36. So then what do you have? Well, 95 is actually pretty close, but you want to get closer. Now here, I kind of cheat a little bit. Let's in fact go up here, divide by 10, divide by 10. So 1 degree centigrade will be 1.8 Fahrenheit. So again, 18 over 10 is 9 over 5, which is 1.8. Well, the cheating comes in because I don't really want to deal with 1.8. So it's almost 2 degrees, almost 2 degrees. So, in going from 35 to 36, let's go from 95 to 97. So how much off is it? It's off by 2/10 of a degree. It's 96.8. So that's how I do it. So, for example, if I were to ask you like 27 degrees centigrade, you'll convert that into Fahrenheit. Well, actually, what I would do in this case, I would go to 30 first, or 30, so 10, 20, 30, so 50, 68, 86. And then I would cheat again. So subtract 3 over here, here subtract 6 for 80 degrees. Now this may or may not sound interesting to you. If you don't like it, then don't do it. But that allows me to kind of do stuff like that in my head without trying to memorize stupid formulas, which I can't do anyhow, and without having to use a calculator. So, in the case of 15 degrees there, let's go back to this, 15 degrees, so 10 would be 50, add 5 more, that means 9 to the 50. That gives us 59 degrees. If you don't like it, don't use it. Okay, so anyhow, back on the record, we'll do this again now. So 0 to 15 degrees.